Welcome to Engineering Dynamics. I'm your host, Dr. Walk, and today we are talking about vector transformation. Vector transformation is used when you want to represent one vector in one frame and represent it in another frame. So basically, we're just taking the same vector and we're representing it in different frames. This is usually done when you're working with relative motion. My students are going to be learning this soon in Chapter 17. We also use it when we're going from a rotating frame to an inertial frame, and that's going to be the substance of this video, is when we go from a rotating frame to an inertial frame, we can use a vector transformation. Usually students, when we start in dynamics, we learn particles, and we do this transformation using trig. So I'm going to run through this example, and when I get to the part where we're taking our unit vectors from our rotating frame and we're projecting them onto our inertial frame, I'm going to kind of give you a hint. Okay, you can actually do this in two different ways. You can use the trig to take your derivative of your unit vector, or you can use the cross product, okay? So I'm going to stop talking and we're going to get into it. So we have this mechanism here, and it is rotating. It is a bar with a collar put on it, and the collar, I'm going to assume that this is going to be an external pin. So this external pin, it is not allowed to translate. So basically what this has is that it cannot move from this position. It can only rotate around, and then the collar can go the entire length of the rod. Okay, it doesn't have restrictions on it. So I'm going to draw two reference frames. I'm going to draw an inertial reference frame, and then I'm going to draw a rotating reference frame. An inertial reference frame, just for review, is a non-rotating, non-accelerating frame of reference. So I'm going to put that here. And note that this frame is not actually attached to the bar that's rotating. It's attached to its origin, so it's not moving, okay? And I'm going to label this axis X and this axis Y, and I'm going to label its origin O. And I'm going to have unit vectors placed here, and it's going to be an I and a J. Conventionally, we do use the Cartesian coordinate system to represent inertial reference frames, and we do usually label the origin O in that type of frame. So that's what I've done here. Now I'm going to locate another reference frame, and this reference frame is going to be a rotating, excuse me. This frame will be a rotating frame. So I can choose between normal and tangential and radial and transverse here, and I'm going to choose radial and transverse just because this has movement along the rod, so I can define its movement in that direction. I can also define its movement in this direction. So this is going to be, I'm going to label this E theta and this E R, and these are my two unit vectors, and I'm going to label this origin E. Okay, so I have two reference frames, and now I want to draw a vector that locates my collar, that locates point A, and that is viewed from the inertial frame. So that's going to look like this. That's the head of my vector, okay? And this I'm going to label R. This green R, this is the vector R that locates point A, and that's viewed from the inertial reference frame. A lot of books will represent it like this. Some books are going to reference it like RA with respect to O. So this is a position vector locating the point A viewed from the point O. Just be cognizant of like both ways of doing it. Whatever I guess your professor wants. Okay, so we have this, and we can represent this vector in the two different frames. The first frame that you can do is going to be, and this is going to, we're going to establish an angle. So the vector R is some theta off of the X axis. So I can represent this vector in the inertial reference frame, and that is going to be some magnitude R in the X, which is going to be cosine theta I, plus some magnitude R sine theta j. And I got this by simply taking one vector I'm breaking it up in its components, and then taking those components and lying them on the axes that I want. So I'm going to take this vector and I'm going to take its x value and I'm going to take its y value and I'm going to project it. And this is what I get. Now I'm going to say, well, what is the velocity of this? Well, velocity is always tangent to the curve and in the direction of motion. So in this case, I'm going to have a velocity of A viewed from the inertial frame. So how do I get that here? Well, I get that here by saying VAO is equal to, and then I have to take this derivative. R is a variable and so is theta. So I can say the derivative of the first times the second plus the first times the derivative of the second, which is going to be actually a negative. So this is going to be a negative R sine theta, and you have to do the inside, so that's going to be a theta dot I, because this is the time derivative. So when you take the derivative cosine, you have to be aware that you have to take that theta out. I think it's U substitution. Then you're going to say plus, and you have to do the same thing over here. So you're going to do derivative of the first times the second plus the second derivative of the second, which is this cosine theta j. So that's what this looks like in the inertial reference frame. This will look a lot better if we represent it in the polar coordinate system. So I can represent R. So let's go back. Let's say, well, RA, so this is my vector locating A, and it's going to be still viewed from the origin, but I'm going to represent it in polar form. And that just means that it's going to be some direction or some magnitude R in the ER direction. And that's it. So comparing this to that, kind of like this better. And then I'm going to go ahead and take its derivative to get velocity. R is a variable and ER is also a variable. Up here, the I and J are not variables, they're constant, and they're constant because they're on the inertial reference frame. ER is on a rotating frame, so it's not going to be a constant, it's going to be a variable. That means that I'm going to have two variables here, so I'm going to need that dot product again. So I'm going to say the derivative of the first times the second plus the first times the derivative of the second. Now, there are two ways to find this variable, and that's what we're going to go over in this video. So let's go ahead and figure out, what does that mean? The first way I'm going to show you is the way you probably already know, and this is going to be the trig. This is going to use your cosines and sines, trig, and the second way is going to be through a cross product. Okay, so those are going to be your two methods of vector transformation that you're going to see in this video. So let's look at the trig first. If we go to our drawing here, we see that we have the two frames. And what you want to do is you want to take your frame and you want to put the origins together. So we're going to take our inertial frame, which is I and J, and I'm going to extend the I axis in its negative direction. And then I'm going to take our second frame, our rotating frame, and I'm going to attach its origin to the inertial frame origin. And I'm going to put it right here. Now, I know that one frame is just rotated by a certain degree. And if I look at our original drawing, that degree between the axes I and the axes ER is a theta. It's angle theta. So I'm going to put on here angle theta. And because of geometry and that this is 90 degrees from here and this is 90 degrees from here, that means that this has to also be theta. So I can say, well, what does ER equal? ER is going to equal, in terms of my inertial frame, all I'm going to do is my vector transformation. I'm going to project the components of this vector onto the inertial axes or the Cartesian axes. So I'm going to take this vector and I'm going to say, what is its I component and what's its J component? Its I component, since it's ER is a unit vector, it's going to have a length of 1. So I'm going to say that ER is 1 cosine theta I plus 1 sine theta j. And E theta, represented in the inertial reference frame, is going to be, and this time I'm going to project down here and here. So this is going to be a length of 1. sine theta I, and that's going in the negative direction, plus 1 cosine theta j. Now my whole job was to take the derivative of this. So I'm going to take this expression, because now I know how to take a derivative of cosine and sine. So I'm going to say, well, what is the derivative of my unit vector r in terms of time? This is going to be theta dot negative sine theta I plus theta dot cosine theta j. Now look at this expression. I have a negative sine I and a cosine j. Up here I have a negative sine I and a cosine j. So that means that this really can be expressed as theta dot e theta. So my answer to my velocity vector expressed in the inertial frame is my velocity vector expressed in the inertial frame using polar coordinates is r dot er plus r theta dot e theta. That's the first way. Now, I want to introduce a second way. The second way is going to be using the cross product. What is the cross product? The cross product takes two vectors, crosses them together, and gives you a third. And that third is going to be perpendicular to both the vectors that you crossed. So if I cross vectors 1 and 2, 3 will be perpendicular to 1 and 2. Let's do an example here. So if I'm going to start with this that I had, because I'm looking for this guy. So I'm going to I'm just going to take it so you guys know it's the exact same thing. I'm going to copy it. I'm going to paste it down here. And this time I'm going to say, okay, well, how do I get this? Well, knowing the cross product, if I just told you that it takes two vectors in the same plane and gives you the third, then I can take this. Let's move this drawing down just so we It didn't take the full drawing, but that's okay. So, and I'm also going to try to move me up here. Okay, so I can kind of use this screen. So let's think about this. The derivative of a vector is velocity, right? So I really have velocity. So d(er) dt, this is velocity. This is the velocity of that vector. So I want to know, if this is velocity, what are two things that I can cross to get velocity? Well, I know that position is going to be perpendicular to velocity, right? We established that here, that the position vector and the velocity vector are always going to be perpendicular to each other, okay? And there's one more relation that I can make, omega. Omega will always be perpendicular to velocity and position. That's because velocity and position lie in the same plane, and those two vectors are going to rotate around the third. The third vector is going to be the perpendicular. So you have a plane, and then you have the third vector, and the two position vectors and velocity vectors will rotate around the third. So our omega is always the axis that's perpendicular to those two vectors. So I need to develop an expression that represents this, because if I cross omega with r, I get velocity, and that's what I'm looking for. So in this frame, my omega is going to be expressed in the third frame, or in the third axis. So one axis is e theta, the other axis is er. My third axis is e3. Okay, it could be ez if you wanted. E3 is nice. And I'm going to cross that with which position vector? Am I going to cross it with theta or r? Remember that I'm trying to find I'm working with er here. So if I have, this is the position vector that I'm looking at, that I want to take its derivative of, so that has to go here. Then I can say that the derivative of er is going to be omega, because that's your constant. E3 cross ER gives you the third, which is E theta. So this here is going to be the velocity of A with respect to O, r dot in the ER direction plus r omega E theta. And omega is just theta dot. So look at these two. You get the same thing. Just one is a lot faster. All you had to do is one line versus taking this, mapping it, and taking derivatives. Okay, so you can take a derivative of the unit vector after you project it from one frame to another, or you can take the two vectors that are known and cross them. And the cross product is shorter, but you can't always use it. Sometimes you will need to use trig, so it's good to know both, and it's good to be comfortable with both. So I hope that helped, and that gives you a new tool to put in your toolbox to help you with your engineering problems. Thanks for joining me, and I'll see you next time.